Students, let's see in short the VLSI design. It will be useful for your revision. So, in the first unit, we have MOS families. In that, we have NMOS transistor and CMOS transistor, and then we have the next topic as so in the MOS families, we will be dealing with the inverter characteristics. What are the inverter characteristics like noise margin, and what are the three operating regions of the transistor? And then next topic will be ideal and non-ideal characteristics. So some characters will be there. We will see it later in while going to the topic. And next, we will see the transistor under static and dynamic conditions and technology scaling. The scaling and all, it is reducing the size. So while designing an IC, usually we will consider these three parameters. That is reducing the size and increasing the speed and reducing the power consumption. So these are the design factors for any design that we need to consider. So if we reduce the size, it will more, we can get the advantage of the compact density. We can have more devices in the lesser area, and moreover, it may also lead to other disadvantages like possibility of short circuits and all. So that and all we need to take care of. So let's look into the unit one. Okay. So first unit. So mass transistor principle. So what is a mass transistors? So when compared to PGAT, mass transistors will be having a high input impedance. So for any amplifier, input impedance should be high, output impedance should be low, and gain should be moderate. So these are the requirements. So while considering this, our MOSFET devices are FET devices are very well suitable for the amplifier design. So there are three configurations: common source, common drain, and common gate. So based upon the terminals that are we are using, if we choose the source as the common for the input and output, then it will be a common source. If we choose a drain, then it will be a common drain configuration for the input and output. So then you will be supplying the input at gate, and you will be collecting the output at source. So these are the main three terminals: gate, drain, and source. So mass, this is the symbol of the mass transistors, and this is the structure. So simply we can have a no need to have the 3D dimension here. Just we can have this like this diagram alone. So this is enough. So for a p type, for a n channel channel must be n type, and the substrate should be opposite character. The channel and the source and drain are the same regions. So if we need to have the NMOS transistor, means our channel should be n type, and source and drain should be higher doping, with higher doping. That's why it is mentioned as the n plus here. So over the channel there must be a oxide layer. The oxide layer is complete, but it should be definitely available at the gate terminal. Over that, the polysilicon gate is deposited. This is the structure of a NMOS transistor. If we consider the PMOS transistor, the reverse ulta will come. So the channel will be of P type, and the source and drain regions will be heavily doped. So that's why it is indicated as P plus regions. Okay. So these is, and there are three operating regions. When discussing the operating regions, there are three operating regions: accumulation region, and depletion region, and the inversion region. So when your VGS is strongly negative, your charges get accumulated. So that's the diagram. You can see the diagrams there. One for the accumulation region, and another one for the VGS less than 0, so that is negative. So that's for the accumulation region. Next one is VGS is small positive. It is lesser than the threshold. Small positive in the sense it is lesser than the threshold, and it is large positive. So that is the inversion region, strong inversion region. So three diagrams for the three operating regions. So under what situation the region is coming? So if it is VGS is negative, it is accumulation region. If it is less positive, then it is mm, depletion region. And if it is more positive, means it is the strong inversion region. Okay. Next, these are the different devices we have, logic gates and all. So different. So this may be asked in 2 marks. Draw the diagram for a NAND gate. CMOS NAND gate and CMOS OR gate, NOR gate. So this I have told you how it has to be coming. So it has to be A dot B the whole bar, right? NAND gate it is A dot B the whole bar. So simply it is A bar plus B bar. For the dot product, I have told you the relationship. For the dot product, PMOS would be in parallel. So since it is so the complement output will be the complement. So A and B are the two inputs that has to be parallel. So we will get if we connect these two, we getting A dot B the whole bar. Similarly, for if it is parallel for the PMOS means it will be series for the NMOS. So this is the diagram for the NAND gate. Stay, and for the NOR gate it is A plus B. So for PMOS it should be series for the addition, and NMOS should be parallel for the addition. So this, in this way they have drawn the circuit. So there may be a possibility of a diagram of these NOR and NAND gates. An ideal characteristics, under the ideal characteristics, the different three different regions you have to explain it. If they ask for the ideal characteristics means, and the source and drain resistances and the capacitances and all you have to write. So that says coming. So where the capacitance will arise, wherever there is a difference in regions. So if we consider the channel, it is N, and if we consider the substrate, it is P. So there is a PN junction there. So wherever the junction comes, the capacitance will arise. So you can see wherever the junction is there, there is a capacitance possible of a capacitance. So if there is a well means it will be having the sites. So for every sites that will be having the capacitance. And non-ideal characteristics, and under the ideal characteristics, oxide capacitance, latchup problem, it is nothing but uh, this meltdown, parasitic bipolar meltdown. uh, so I will here it is. Latchup can be triggered when transient currents flow through the substrate during normal chip power off. Even in the supply is off, there may be a current flow, so into the substrate, which is called as latch up currents. So this is the area where we have to look up what is for the latch up can be triggered when transient currents flow through the substrate during normal chip power off, or when external voltages are being applied. So this is the latch up situation. And for avoiding the latch up, these are the suggestions we have to give. So to avoid, so this may be important to mark what are the conditions that has to be met to avoid the latches. And what is channel length modulation, I have these all I have marked for yourself. So channel length, it and the effective channel length is getting decreased. So that is the channel length modulation. And subthreshold conduction, when the applied voltage is less than the sub threshold voltage, we call that to be a subthreshold region. So in that region, what is the drain current? So I have write down the equations for the drain current in all the regions. And junction leakage, wherever the junction is, there will be a leakage of current flow. And tunneling, so tunneling is in the sense means you will be having a energy band diagram. So valence band will be on the bottom and conductor band will be on the top. So in between you have a in between you'll be having a Fermi gap. So in this may you might have heard in you might have studied in the insulators, sorry, the structure of conductors and insulators. So for conductors it will be overlapping, and for insulators it will be far away. So this will be the situation. So if the layers get aligned so that there is a free flow of charges, then we call that to be a tunneling. And temperature dependence. These parameters are temperature dependent. So mobility, and mobility is also temperature. It is varying with the temperature, and the threshold voltage is also getting varied by the temperature. And body effect means, so the voltage difference between the source and the bulk. So the substrate potential should be zero. So that's why I have mentioned here VSB must be zero. If it is not maintained at zero level, then the threshold voltage and the channel length is getting affected. So this is body effect. And next you have the transconductance. Transconductance is nothing but I by V is your transconductance. And threshold voltage, if we increase the voltage beyond threshold voltage, what will be the uh, nature? That is discussed here in this threshold voltage. And mobility. So mass figure of merit, it should be transconductance divided by the capacitance. So it is depending on the this mu is the mobility factor, and this tau n is the propagation delay. So if we consider the MOS transistor, NMOS inverter, these are the three different regions. So you may have in the diagram. So there are five points where A, your PMOS is on and NMOS is off, and P, PMOS is getting moving to saturation region like that. So here you can see the different regions. It is in the active region, it is in the on state, and NMOS in the off state. And for the P, it is in the linear region, it is getting moving to saturated. For the C point, it is both are in the saturated region, and for the D point, it is moving towards off. It is moving towards on. NMOS is moving towards on. And what are the conditions? What are the output voltage situations? V out will be for PMOS. Actually, if we are applying zero means PMOS will be on. So VDD output will be inverted. Zero, for zero, it has to be produce high output. So output is VDD. So that is shown in the table here. Okay, V out is less than greater than or equal to half of the voltage at B and C. And for last E region, it is becoming zero because we are applying data 1. So for NMOS will be on. So this will make the, if your NMOS, this is the structure. If your NMOS is on means your supply will go down to ground. If your PMOS is on means it will, the supply will go to VDD. That is the situation. That's how it is operating. And beta effect ratio, this beta n by beta p should be maintained high. The inverter is high skewed. If it is less than 1, the inverter is low skewed. So this is different situations. And technology scaling some parameters, this I have framed the table and given to you. If you haven't got, get it from your students. I have merged all the table into a single table so that it will be easier for your study. So transistor scaling, under the transistor scaling, lateral scaling means only the gate length need to be considered. That is gate string. That is, you can see it here. Gate alone has to be changed. Transistor scaling, all the dimensions are changing. Device voltages, doping concentrations, all the parameters are being changed. In lateral scaling, only the gate and constant voltage means the voltage is made constant. The other features are made varied. So this is the interconnect scaling. So here also you can see the all the dimensions are keep the wire height constant. Wire height is made constant, and so these, how it is being increased or decreased, I have suggested you earlier. And power consumption, how much power is being consumed. So the total power consumed is, the average power consumed is dynamic power plus short circuit power, leakage power, and static power. And dynamic power is due to the charging and discharging of these transistors. And short circuit, there may be a possibility of straight connection of in both the NMOS and PMOS. This is your PMOS, this is your NMOS, both are being on the in the on situation means there may be a possibility of straight connection to the ground. So this is called the short circuit current. And leakage, wherever the junction difference, there will be a leakage. And static power dissipation is also there. So the, what are the approaches we have? This is another important to mark. What are the power reduction technologies we have? So the reduction of the output capacitance. In these ways, we can reduce the power consumption. And dynamic power consumption, we can reduce the dynamic power consumption. And similarly for short circuit power dissipation also, there is a here it is. You can see the reduction in the soft is achieved by applying various techniques. So by proportional to, P short is linearly proportional to the input and the signal rise time and fall time. So if we if we alter the capacitances which affect the timing, we can change the short circuit power dissipations and leakage power dissipations wherever the junction is there where the leakage current is flowing. And diode leakage current, these are the other parameters, non-linear parameters. So the under the power dissipation, what are the different leakage currents we are discussing? Diode leakage current is there, and subthreshold leakage current is there, and induced current leakage is there, and gate oxide tunneling is there. These are the different types of leakage currents. So these are the different reason for the power dissipation due to leakage. The power leakage power it is. So the last power is static power dissipation. So static power dissipation is so ideally there is no static power, but due to the actual operation, if it is differing from the normal operation means there may be a possibility of static power dissipations. So that's it. So I have suggested what are the important terms, what is channel length, and how latch-up problem can be overcome, and what are the methods to reduce the power dissipation and all, and steps involved in IC manufacturing also may be asked. Hope you are clear with the unit one. We will continue the next unit.